So you can use Apache Kafka as an event bus, right? Events get produced to it, they sit around there for some number of milliseconds or minutes or months, and then they get consumed out. But if that's all you're doing, I think you're selling Kafka a bit short, because sooner or later, you're going to want to start processing those streams, transforming the data and joining it and aggregating it. And there's actually a lot of support for doing that if you get into the world of stream processing. But stream processing is one of those things that can be harder and easier than you think. So in this episode, we're going to talk to Jeff Bean and Matthias Sachs about different approaches to it, why it can be hard, and how things like KSQL and Flink can make it easier. And somewhere along the way, we end up discussing XML and COBOL too. Before we get into it, Streaming Audio is brought to you by Confluent Developer, which is our site that will teach you everything we know about Kafka and stream processing, including some step-by-step tutorials for some of the things we discuss in this episode. So check it out at developer.confluent.io. And if you want to start a Kafka cluster running for your own stream processing project, head to confluent.cloud and register with the code podcast100. You'll get $100 of extra free credit and you'll be up and running in minutes. And with that, I'm your host, Chris Jenkins. This is Streaming Audio. Let's process some streams. My guests today are Jeff Bean, who is the Technical Marketing Manager here at Confluent, and a former evangelist of things including Apache Flink for data artisans, and Matthias Sachs, who works on Confluent's KSQL project, among other things. He's got a PhD from the University of, where was it, Matthias?
Humboldt University, Berlin.
Humboldt University in Berlin. Gentlemen, welcome to the show.
Thank you. Hi.
So you've both got backgrounds in, obviously, Confluent, KSQL, but also Apache Flink and some other Apache projects. Let's go right back to basics and see if we can trench through the world of stream processing. So my idea of stream processing, my naive idea, is I've got Kafka running, this is great, I write a consumer, I write some code that starts chewing through a piece of data and spits out events on a producer. I'm done. That's stream processing, right? Consumer, producer, bit of processing. Why is that not the whole story? Why do we need anything more than that, Matthias?
There are multiple things about that. And in particular, I would like to mention two aspects. One is stateful stream processing. So if you have to manage state, then your program just becomes like 100x more complicated. And building this yourself is quite challenging. And the other one is exactly once processing. So it's also very challenging. I mean, the producer and the consumer in Kafka expose low-level APIs, but it's also not straightforward to use them correctly in this setting. And so higher-level abstractions actually makes this part much easier.
Okay. Perhaps we should tackle those one at a time. And I'm kind of scared of exactly once processing, so we'll leave that technical data until we get a bit later. Why is state harder? Give me an example of a stateful application and tell me why it's harder.
Yeah. In general, every time you want to do something that is context dependent and basically includes more than a single event, then you become stateful. So that could be an aggregation over a time window, or maybe a global aggregation, or if you join data, or if you just need to remember an event from the past to make a decision in the future and a new event comes in to, do a certain action. And the problem is, of course, or this is a naive way, is to just, use a hash map or something like that, put your key-value pairs in. But then, of course, if you have any error, then you lose your state. So you want to make the state fault tolerant. But how do you do that? That's the main challenge. Another naive approach would be, I write it to local disk. Mm-hmm. But then, of course, you need to restart on the same computer to make it work. Or you say, I attach remote storage. Then you can, also use a different computer, for example, if you're in a more like stateless environment like Kubernetes or something like that, where you deploy your stuff. But then you have remote state and you have more moving parts. So what happens if your network connection to your remote state goes away? Then you again have a problem, right? That you need to take care. And then you basically come from one problem to the next problem to the next problem. And it's just like very, very complicated.
And it seems to usually works in such a way where you solve the immediate problem, and then you chug along for a while, and then you realize you have some higher level problem or some next problem, and then it works. So a simple aggregation, maybe you don't need a whole lot of state for that. But now you want a rolling aggregation with a time window, or now you want to enrich data by joining it to another stream, and suddenly you have to code state in a way that's also, like Matthias said, fault tolerant, but also distributed and scalable. And this becomes very difficult just in and of itself, and you start needing a whole framework for that. And then when you actually start relying on the framework, how do you keep the framework accessible and easy to adopt so that you don't have to learn the complexities of reasoning with time and building out, different state backends and the strengths and weaknesses of each one, and so on, just to get your application out the door.
Okay. So you've both spent some time with solutions to that problem of the increasing complexity of your stream processing, right? Give me a quick overview and then we can dive into the depths. What are the different ways of solving this?
Want to take it?
Who am I going to put on the spot?
Well, it's a very wide question. So you would use frameworks for this, right? So are you talking about different ways of addressing the stream processing problem? I think when you're coming at it from the point of view of a developer, you want to use the best framework for the problem you're trying to solve. Apache Flink is very attractive for that because it can do a lot. It's very capable, and it has a lot of these constructs that allow you to reason about things like state and things like time, and so on. But then when you come at it with another angle, which is maybe that of a new user or someone who's just gotten their arms around consuming and producing events with Kafka, and now they want to do the next thing. Now they want to do some basic aggregation, and then they want to add a time window. But they want to do it without spending months learning a development framework. Then you start looking at SQL-based stream processing, such as ksqlDB or Flink SQL. Right.
So take me should we do the low-level version first? Yeah, let's go with that. Take me through what a Flink stream processing application looks like first. Teach me something about that.
Sure. Matthias, or do you want me to go, or do you want Matthias?
Go ahead, sure.
Okay, so Flink is implemented in Java. There's a streaming API that's layered on top of Flink. Flink has multiple API abstractions, so it's layers upon layers upon layers. At the highest level, there's a data stream API where you define the data stream, and then you define operations that you're performing on the data stream at the API level. So you open the stream, you open connection to state. As you process the stream, you store things in state, and then you can define different operations like windows and so on. And those things get compiled into operators that run in the Flink engine. Very similar to a very similar distributed architecture like Apache Kafka.
Okay. See, I don't know Flink very well at all, but I know Kafka Streams. That sounds very similar. Matthias, is it broadly similar?
It is absolutely. I would say 80% of use cases and 90% use cases. You can pick the one or the other. It doesn't really make a difference.
Well, that's interesting. What's the remaining 20?
Yeah, so the main difference is really the deployment model from my point of view. So Kafka Streams is built as a library. So you basically say, I embed it into my regular Java application and embed the compute in my Java application. So a very natural pattern here is microservice architecture. You build a lot of small microservices, embed the compute, you're done. Flink, on the other hand, has a cluster model. So there you basically need to set up and deploy a Flink processing cluster. And then you basically write your job and you submit the job into the cluster.
Okay.
And then it's running in the cluster. So you basically have more like a server-side processing model. And then, of course, that's similar to ksqlDB. ksqlDB will also say you deploy a bunch of ksqlDB servers and then you submit your SQL. So there are really the differences here about client-side processing or server-side processing, if you wish.
That must change the way you write your applications, right? Because if it's a library, there's going to be more. I assume there'll be more mixing and matching between stream processing code and your regular application code.
Yes, that happens a lot, especially when you want to tap into your state. So in Kafka Streams and ksqlDB, we both allow you to query state ad hoc. So in Kafka Streams, we call it interactive queries. In ksqlDB, we call it pull queries. Do an aggregation, you build a table, and then you can query the table directly. I think Flink had a similar thing at some point. They called it queryable state. I'm not sure if that's still maintained. But then, of course, here you would actually start to query remote state because your application is running server-side, so the state is on the server.
Yeah.
So it becomes a slightly different pattern.
And the state is also a different backend. Usually it's RocksDB or something else. And you can swap it in and out, which is fine, except the behavior of the application changes depending on the state backend. So now the developer building the stream processing application has to worry about how the administrator has deployed the backend. And if you swap that out, then your application changes. It becomes a bit of a troubleshooting nightmare.
Right. Hang on. Step back a second. Where does RocksDB even come into this? Why do I need another database?
To some extent, it's an implementation detail. On the other hand, it's not. And I mean, the fault tolerance mechanisms in Flink and Kafka Streams ksqlDB are quite different. So in Kafka Streams, we basically started out to say we don't want to have a lot of additional dependencies. And we do already have a Kafka cluster. So what we do to back up state is we create an additional topic in the Kafka cluster that we call a changelog for the state. And every state modification is also written into this topic as a write-ahead log. Mm-hmm. And then, if we lose the state, then we can replay the changelog topic from the Kafka cluster, and we're fine. And because the cluster is there anyway, because it's our input and output, there's no additional, dependencies. Flink is choosing a different approach that basically say you configure a so-called state backend fault tolerance storage that could be an S3 or an HDFS depending on your environment. And then what Flink is doing is basically says, well, when we have those RocksDB files that store local state, we actively copy those RocksDB files into the remote store. And then when we need to recover, we can copy those files back.
Okay. Is that done right ahead as well? Or have you now got a transactional thingy going on?
It's kind of a write-ahead thing as well. So yeah. Flink also has a mechanism of committing. Where you would say, I note how much input data I have processed in Kafka, committing offsets. And before you do this, you would basically say, first copy all those files. Or in Kafka Streams, ksqlDB land, we first flush all pending writes into the changelog topic to make sure we don't lose anything. And only after that, we commit the offsets. And that basically gives you then at least once processing semantics.
Okay. So I see. Yeah. So I was going to ask how it is that when it's a library that you're running inside your app, it can actually do distributed storage. And the answer is reuse Kafka, write it to a topic, right?
Right. Exactly.
Yeah, that makes sense.
That's the Kafka Streams answer. The Confluent answer is Kafka becomes sort of the equivalent to the state backend. There are a couple of times when I was working with Apache Flink where this is really inadequate because the amount of traffic that is required for the stream processor to actually manage state and the number of reads and writes to the state backend start dwarfing the amount of just normal Kafka traffic. In that case, now you start wanting to separate the backend. So I think of this more as an anomalous use case or sort of a special one, rather than kind of the default, which is Kafka's fine, store your intermediate data in Kafka and it's fine.
Yeah. Okay. Yeah. I see how that throws together. So that gives me a sense of how these things are operating on the back end. Jeff, how is my life going to be seriously different apart from the deployment model as a programmer using these stream processors?
We're using either Flink or Kafka Streams.
Yeah. How's my life going to change?
So the framework is different. The APIs are different. The interfaces as a developer is completely different. I can't really arbitrarily switch from one stream processor to the other without rewriting my application. That's why it's kind of critical to make a good decision early when you're building these things. I would there are strengths and weaknesses to each. I would suggest that working within the same platform for your stream processing and your event streaming is a good place to start, right? You don't want to begin consuming and producing with Kafka, come across a stream processing requirement, and now go learn an entirely separate distributed system, right? Which is kind of what adopting Flink would require. A lot of Confluent customers actually are not doing stream processing yet. So there's plenty of room to grow in the platform just to, without needing to go adopt something else. You kind of have to hit, in my view, you have to hit a brick wall of some sort before abandoning the platform altogether and going to some other stream processor. And then Flink has quite a learning curve on this. I was doing evangelism and education for Apache Flink for about 8 months. 3 to 5 of those months was just learning the basics well enough to teach it to someone who knows absolutely nothing. So there's a significant investment in that when you select a technology, which is, I think, not to be understated. If the productivity you're going to have by your development teams and your data teams is going to continue to grow, and your team is going to continue to be effective if you can stay within the same platform.
Yeah. So that kind of leads us on to the motivation, like the mental on-ramp, the motivation for having an SQL-like interface, right? Because to a certain degree, you can kind of assume that all programmers know some SQL. Mm-hmm. But take me through that evolution from saying, okay, we've got it as a library, now we're going to jump into supporting SQL, KSQL. How did that come into being? Jeff, you're the product guy.
Sure, I think it's a trend you'll see in a lot of the stream processing space that's out there. Is you want to make it simpler. I've already dinged Flink a few times for being difficult to learn. Arguably, a developer you should not need a developer to do stream processing, right? Arguably, you should be able to take a data analyst, right, and take their existing skills and be able to process a stream much like they would issue an aggregate query against a database. So that's kind of the dream. And that's kind of the requirement that we're all sort of chasing in order to lower the bar on stream processing. Flink has Flink SQL. It's a project that compiles a SQL query into a Flink job and then deploys the job to a cluster. We have ksqlDB. They're similar on the surface. One of the things that ksqlDB offers, I think that's makes it a cut above, is the integration with Connect, so that I can define a connector and a ksqlDB query, load that data from that connector into a Kafka topic, and then query it right away, and then sync, define a sync connector, and write the result out to something else. So I have my whole end-to-end data pipeline in a single query or a series of queries. So that's one of the things that I think ksqlDB benefits from, is I can do more faster. It gives me more value quicker. I think on the Flink side, they've really spent a lot of time being able to express complex ideas. So there's an API or a function or a series of functions in Flink SQL for complex event processing, where I can actually define a series of events by how they look and then process them as a chunk in a ksql or in a Flink SQL query, which is interesting. And they also
give me an example of that. Sorry to interrupt, but I make that concrete for me.
Okay, let's say I'm tracking trips, taxi trips, and a complete taxi trip might be a start event, a series of stop events, and then some final end event, right? And then maybe at every stop event, there's a charging event, right? So I have a series of events that together have meaning. And I want to sort of identify those together, even though they're spread across over time, and then process them as a unit. I think you can do this in ksqlDB as well with the table streams duality. You can define tables and have each event type be a row in that table, and then query the tables together. But the way Flink has you reason about it is with this complex event processing language. So that's one aspect of it. So it's this trade-off between complexity and ease of use and ease of adoption.
Okay. So that, Matthias, that kind of brings me into the great thing about adopting SQL as your front end, as your interface for stream processing, is it's going to feel very familiar to people. but it's not the same. When I log into KSQL, I'm not getting Postgres.
Yeah.
So let's do a survey of that. What different concepts are there under the hood, and what do I have to actually adapt to as a user?
Yeah, absolutely. So I think the main difference is really that SQL was built for kind of static data, if you wish. So I mean, you have your tables, and you in an ad hoc manner, issue a query. And at this point, sure, there might be concurrent transactions, but in the end, your query more or less runs on a snapshot of the database.
Mm-hmm.
And so you have a finite data set. So the query, computes the result, returns the result to you, and terminates, and that's it. In stream processing, we want to do this quite differently because we basically say, well, we want to have like a standing query, right? That is computing all the time. So you have potentially infinite data. And especially in ksqlDB, we go at different routes than Flink. So we basically really say you have two objects. You not only have tables, you also have data streams. So you can say a create stream statement and a create table statement. And then when you query the one or the other, you also get different semantics because a table is basically this evolving set of records, that change over time.
A lot like a
database, but the query really, tags along with the changes instead of executing over a snapshot. But then on the other hand, you have this stream, and a stream is basically an immutable sequence of events. So there are no updates. So the semantics are different as well. And that's also why we expose different operators. For example, if you join two tables, well, you just join two tables, and whenever the input in one of the two tables changes, then you just update the corresponding result. So straightforward, like we would expect it.
Yeah.
If you join two data streams, you can't really do that anymore because, well, data streams are infinite. So here's a language we basically say, no, we enforce you to limit the scope of the join using a join window to basically say only join events that are in time close to each other. Because otherwise you need to buffer everything, right? And the input is infinite. So, and here you see this different semantics shining through because when you say join stream 1 to stream 2, we force you in SQL to say, specify the window. In a table, you don't have this clause. And then SQL starts to diverge. And you really need to understand if you query a stream or a table because the query will behave quite differently.
One of the things I find really interesting about SQL-based stream processing in general is the limitations that people run into conceptually. And I have examples on both sides. When I was teaching Flink SQL, I was at a large web-based company that is not to be named, teaching a Flink class. We were talking about Flink SQL. And the person in the class had a Flink SQL job running. It was very slow. And we were able to go and use Flink techniques to go in and debug that job and figure out that the parallelism was not high enough. So the solution was to increase the parallelism of the running Flink job. You can't do that without killing the query and reissuing it and starting it over again. And that led to sort of a downtime. So there's that limitation on the Flink side with SQL-based stream processing. On the Confluent side, one of the strengths of ksqlDB is being able to connect to other systems and also being able to have a nice front ends to it. So any application that emits SQL, whether think of a business intelligence application or an analytics application of type, can emit ksqlDB statements that work. And we have proof of concepts that work. We have partners that do this. I was in a meeting with a product manager for an analytics company, and she basically asked, she said, I don't understand how this works, though. Like, if I emit ksqlDB queries and stream the result to my dashboard, like, what does the customer do? Do they watch it like a TV? And that's like good stream processing, or is it something else? And like, they were looking to us for that answer, and we were looking to them for that answer. Like, we're giving you the SQL-based front end, right? And you get to do what you want. And
what do you fancy?
So I find it really interesting that we're trying to make things easier and easier to adopt and easier to reason about, and then we run into these kinds of not exactly limitations, but what's the right answer to these kinds of questions? I think it's still to be determined.
Yeah, I think you see that. I think you see that in functional programming. You need a different mental model for dealing with, in some cases, infinite lists of immutable data, right? And then you see it in front-end programming where, okay, you can poll an HTTP endpoint and get a snapshot of the world, and that's one way that will influence the way your UI is designed. Or you can connect to a WebSocket, and you have to deal with this infinite stream of stuff happening to you. And it's not that they're technically wildly difficult concepts, but they're so unfamiliar, you have to rewire the way you think about application building.
Yeah, I totally agree to that. I mean, so the point is really it's a mental shift for developers, especially because if you're used to a database, just to have this idea of a query that doesn't terminate is like kind of alien to most people. Right. And the dashboard example from Jeff is just like, perfect. It's kind of, well, okay, it's streaming the data. So what do I do with it? I mean, and that's the point, you need to re-architect your application from ground up to basically, integrate with stream processing. You change, just not say, oh, I used Postgres and now I drop in ksqlDB and everything is just fine on the front end. No, you need to re-architect everything.
Yeah, because and it's not like you need to re-architect it because you've switched library. You've switched mental models. You've switched the way you structure ideas.
Exactly.
And I guess the primary payoff for this is the real-time aspect, right?
Yeah, also, yeah. And I mean, it's not just real time, it's time in general. I mean, stream processing is basically always has a time dimension to it, right? And that's also a very new concept, and it's hard to reason about. And there are also different concepts that are exposed. So Flink is using this watermark-based approach to reason about time. Kafka Streams is using a so-called slack time approach with advantages and disadvantages to both. But in the end, it has always time. And especially this concept of event time is quite new to a lot of people, because most people, if they look at time, they think about wall clock time. So let's say you do a window aggregation, and then you say, okay, my input could have out of order data. So, the window end time is reached. So I wait for another 2 minutes and then the window closes. Well, that might not really happen if you do everything event time based, because in event time, you just don't want to wait for 2 minutes wall clock time. You want to wait for 2 minutes of event time to pass by before you close the window to give you deterministic processing. And then, reason about this new event time concept and dealing with out of order data in event time and stuff like that can be quite challenging. And there actually also is where SQL comes into place and helps a lot, because we try to have higher level abstractions where many of those things just work out of the box, while, the lower level programming you do, the more you need to take care of those things manually. So going back to your original example, okay, I use a consumer and a producer and I do my stream processing myself. Well, then you have to think about all those corner cases.
Yeah, so that's one way you can go and get your own PhD, right?
It gets highly relativistic very quickly, right? When you're talking about, you think you're reasoning about time in your consumer or your producer, but now you're realizing, okay, this event was generated on some device on some part of the planet, and the time on the wall clock for that is one thing, and then the time is the event that the device stamped on the event was another thing. And then there's the time it got to Kafka, and then there's the time it gets to you, right? And then you throw in Flink, and then there's the time it gets to Flink, or some other stream processor, and it starts becoming very mind-dizzying very quickly. And it kind of works against this whole idea of making stream processing accessible. I love Flink because it lets you reason about all this stuff. Like I can swap in time semantics with one line of code change. I can switch from system time to event time. But the ramifications of that and how you tell that that's correct is really on you, and that's painful.
Yeah, again, that reminds me of the kind of relational database world where you've got those different serialization guarantees, like read uncommitted and read committed. And you've probably read about them, and you probably just stick with the default because it's too much brain space to spend, right?
It depends on the kind of developer you are, right? I mean, maybe you stick to the default, or you think this is most definitely not going to work for me, so I have to build my own time management system. In the very short time I was working with customers using Apache Flink, I ran into two developers who decided to build their own watermark extractors because they didn't understand what Flink was doing, so they thought they had to write it themselves. They were both doing it wrong. I didn't understand exactly how they were doing it wrong. I had to go bring in a Flink committer who had to tell me they were doing it wrong, and then he was able to tell me how to use it correctly. Again, it's one of those things where when you're given too many tools in a space that's hard to reason about like this, it becomes difficult to be effective.
Yeah. So, Matthias, I'm in the mood for some gory details now. So let's peer a little bit behind the hood. And maybe by the end of the explanation, I'll be not so in the mood for gory details and I'll just go with SQL. But so different types of time-related joins, one I find interesting is a session join. So I want you to explain what that's actually doing. Let's peer a bit under the hood so I can see how complex this soup is, right? Session-based window joins.
Well, I mean, joins don't really have sessions in our API. I'm not sure if Flink has anything like that. So, I mean, we have session windows for aggregations. And there's the idea is to say that it's a little bit similar to the taxi example Jeff gave before, but still different. So you basically say, I track the data, and if events are in close to each other in time, I put them into the same session and process them together. And then if there is a gap of inactivity, then I actually say, I split those data into two different sessions. So for example, if you have a user logging in onto a website, then you could say, if the user becomes inactive on the website for, let's say, 10 minutes and doesn't, do any interaction, then basically the user session ended. And then I take all the events inside the session for this user, and I can do something with it. And then if the user comes back, it just start a new session for the same user. So you have basically the user-based split out for, you process each user individually, and then you apply those session detections basically based on time. If you join, you just say, I have two input streams, and I just have, in the end, an additional predicate that tells me how far in time those two records from the left and the right input could be apart from each other. And if yes, it's part of the join conditions, they're allowed to join, plus an additional actual join condition on the data you want to use. So you have a time condition and a data condition, and then you put them together.
One of the things that I think is, just to add on to the example that Matthias just mentioned, is you capture a bunch of events from the first session closes, the user comes back, you're having the second session, but then the stream processor gets an event from the first session because things are late and things are out of order, and now it's up to you as the application developer to figure out where to put this. Do you discard it? And each framework will behave differently in this respect. One of the things Flink can do is it can identify that second event or that later event from the first session, re-aggregate the whole first session, and re-emit everything. But now as the application developer, you have to understand that it did that and understand what that means.
What's the KSQL answer to that question?
Yeah, it's very similar. I mean, in general, ksqlDB has a little bit of a different model when it comes to emitting data. So Flink is using this watermark approach, right? So you basically say, I hold off to send any output until I see a watermark. So in the example Flink gave, you basically say, I have the session, I accumulate data, but I wait for the future. And if this out of order event arrives, I add it to the session before I actually trigger the computation. Okay. And then, of course, in Flink, you can also, after the fact, actually re-trigger the computation if you keep the state around. And so ksqlDB uses a different model. ksqlDB basically says, well, every input is basically a change to your result. And so the output is also modeled differently. So in Flink, if you do an aggregation, you always get a table. And the table basically contains a row per session in this case. And then every time an input record comes in, we identify the corresponding session based on its time and user ID, for example, and then we just update the row. So you basically have this kind of state that is updated continuously in ksqlDB as a table, while Flink would say, no, we accumulate all the events, and in the end we give you one final result and send it downstream.
That must have latency implications, right?
Yeah, absolutely. But I mean, that's the way it is. If you say, I want to have a single final result, then you just need to wait, until you can make a decision to say, okay, I'm done, I've seen everything. And because that is very hard to answer, we follow this different approach to say, well, we just, incrementally maintain your result. And then as an application developer, when you let's say, query the table, you make a decision when you want to receive the event. And then you need to reason, is this current result fresh enough for me, yes or no? Or do I actually wait longer to query the data? But we just incrementally, maintain the result for you and basically make it available to you. And it's up to you to use it or to wait and use only a more recent one later on.
Yeah. So
but the problem doesn't go away. It just, shifts from one place to another place.
Yeah. It's whose pain it is.
Yeah.
So you're in this situation where you've got the live state in a KSQL world, but you have to accept that the client may reconnect later and things will change.
Yeah, exactly. And of course, in ksqlDB, you can also have a cutoff point where at some point you say, I don't accept any changes anymore. And then those new input events that are out of order would just be dropped on the floor, and you basically freeze your state and say, that's it, I'm done.
Yeah, you're too late.
Yeah, exactly.
And are these all things you can say in KSQL, all these different settings?
Yeah, exactly. So in ksql, we express this as a grace period clause. So when you do your aggregation, you specify the size of the window, or for a session window, the get parameter of inactivity. And then there's an additional grace period clause that tells you how long you're willing to accept updates to the state. And after stream time is passing the grace period, basically window end plus grace period, then we basically just freeze the window and it's immutable.
Yep. Like going to the cinema, you've got a start time and you've got to get in before the trailers finish. And if you're not there when the film starts, it's too late, right?
Exactly.
That's a bit of a stretch of a metaphor, but I'm going with it. So that takes me into thinking, right, here you are, you've decided to put an SQL interface on stream processing. I'm sold. Good idea. And you've got a lot of syntax that you're just going to reuse, right? But maybe this is a question for Jeff. You've then got a product design piece where you're taking a familiar syntax and adding to it and adding new concepts and trying to teach people in a feeling familiar way. How did you go about the whole process of that developer experience design for SQL Plus?
It's a good question. I think the first thing you want to do is be able to handle the basics, right? So I want to be able to define most, if not all, the use cases for my stream processor in my higher level language. So I want to be able to create a stream or a table, have those constructs defined for me, define how to populate that stream or that table. I want to have all my most common aggregations. So I want to be able to define a time window and then declare the different types of time windows. And I want to be able to define queries on that. So I want to have derived queries. This is much how SQL works. And then there's room for new stuff, right? And how I define this new stuff, I think is also interesting. You can do things, you can move the language along quickly so that you can get easier adoption, or you can go for sort of the standards-based, legitimate kind of approach where you try to actually revise and evolve the SQL standard so that anyone who does ANSI SQL version X actually has a stream processing construct. That one I think takes a lot longer, and I don't think everyone who cares about SQL cares about stream processing. So this is another place where you see the two technologies diverge a little bit, right? Confluent ksql, the language itself is not concerning itself so much with evolving the SQL standard. Whereas on the Flink side with Flink SQL and Apache Calcite and others, they've really have dug in on this whole standards question of really, they're starting to write academic papers on revising SQL for stream processing and all of this. And I think that's interesting and great. Who knows how long it will be until we have enough consensus that you can have this be standard from technology to technology. I'm sure at the end of the day, what you'd love to be able to do is use the same SQL-based language and swap out the backends based on whatever you need. I don't think we're there yet.
Yeah, I'm not convinced we ever will be. It's like there was I don't know if it's still a thing, but for a while there was this dream in Java that you would write one interface file and just swap out Postgres for Oracle for MySQL. And it never works because you always pick your database based on the features of that database, right?
Yeah, and
there's always something that you want that you can't get rid of.
I heard an executive say something once, like when you're like clearly in the lead, you don't care about the standards, and all the followers are going to try to use the standards question against you, right? So I think this is an indication that Confluent is clearly in the lead in terms of ksqlDB and sort of SQL-based stream processing. But another thing I heard actually a Flink committer say, and this was in reference to Apache Beam, which is like another abstraction layer for stream processing that's API based. One of the tech critiques that he has had, which I think also applies to SQL-based stream processing, is one, if the abstraction layer isn't working for you, the first thing you do is get rid of it. And you actually get back to the brass tacks. So it's interesting. And in that regard also.
Yeah. Okay. So that raises a difficult question then that I have to ask. Matthias, is probably a good one for you to field, right? So where are those holes? I mean, I assume KSQL is still evolving. Where are the gaps in the road where you would have to dip down into something like Kafka Streams?
Yeah. There are a few things. I mean, very often you want to be a little bit more like imperative. I mean, SQL is a great declarative language, but with higher level abstractions, there's usually, I mean, it's easy to use, but there's also more limitations, right? You cannot express everything. And so one good thing is really if you want to do something on a periodic time scale, either event time or workload time. So both Flink supports this. They have a so-called timer API, and Kafka Streams supports this as well with punctuations. Where you just say, I register this callback, and I want to re-execute this callback, let's say every 5 seconds in workload time, or every 20 minutes in stream time. And then I want to do something, modify my state, clean up my state, or stuff like that. So that's a concept we don't have in SQL at all, because there is no kind of a callback you can register, right? And what would it even mean? And how would you embed it into language? Because in the end, you say, select star from whatever,
Yeah.
So it just doesn't fit the model. So that is, I think, one of those things. And another thing is also, I mean, usually you also have limitations, what kind of data formats you support. So ksqlDB, supports Afro and JSON and of course the native Kafka. But then some people say, hey, I'm still from the 90s. I have XML data. And ksqlDB is just like, well, sorry, I can't parse that. We haven't built it. And then when you fall down to lower level APIs, you can always do this, or if you have your own, whatever weird format or whatever, then it's much easier to integrate. Teaching a database also the formats is much more challenging. Also, when it comes down to data types and things like that, you need to define those translations because SQL has its own type system, There is an integer and a varchar and a big int and whatever. And then it's kind of, how do you even translate between those different data types?
Matthias, you mentioned I'm the user who's still in the 90s. When I was doing partner work with Confluent, we were doing mainframe integration, and I had a customer say, well, I'm still in the 70s, and I have COBOL copybook data that I want to ingest and streaming data with Kafka. And it's like, it becomes, again, really important to be able to work within the same framework. I can at least bolt a connector on that, ingest my whatever wacky data format I have into Kafka, and then use a stream processor or a single message transformer or something to get that into some uniform process that makes sense.
Yeah. So there's somewhere out there, there's someone writing the connector for SOAP, right? The flavor of XML that was even more obtruse.
Yeah, absolutely. I think that really is the main challenge in here. And once in a while, it's also just easier to express some very custom logic. I mean, ksqlDB also, of course, supports UDFs. That is very helpful and can close the gap here in a lot of cases. But once in a while, if you roll your own stream processor, especially if you want to really more complex state manipulations, where it's not just aggregations and joins, but you basically say, for every input record, I want to do some custom logic based on what I have seen before and what is in my current state. And then I modify the state. And then I also trigger some output events. So you have kind of you could say a state machine model, right?
Yeah.
Then implementing this in a Java function where you just have a callback for every input record and you get your state and you just modify it. It's much easier than expressing something like that in SQL.
Yeah. Do you think it's coming? Are there plans to do that sort of thing on the SQL side?
I'm not convinced that it's not doable, right? I think there is a way to model, use the stream table duality to model a table which represents your callback architecture and then query that and show I think it's possible. It's just not as intuitive, right? And in the using the taxi trip example again, if I am looking to run a query for very, very long trips, maybe taxi trips longer than 6 hours, right? It's very intuitive to do that with a timer model. Every taxi trip start, I start a timer, and then every taxi trip closed, I close the timer, and then if the timer goes off at 6 hours, and there's my report, right? I'm not convinced you can't do it. I just think it doesn't fit how we think as easily.
Yeah, I tend to agree to that. I think actually SQL itself is like Turing complete, if I remember correctly. But do you really want to use it in this manner? I'm not sure.
I don't know if you've heard of this. There's an annual coding challenge called Advent of Code that happens around Christmas time every year. And an old friend of mine used to try and solve, it's 24 puzzles in the run up to Christmas. And he used to try and solve every single puzzle just using SQL, which is phenomenally difficult. And most days he managed it. So I believe it's Turing complete. I also believe you don't want to do that for anything
so,
other
but it's, as Jeff said, it becomes not intuitive at some point. If I can just once in a while write a for loop and nest with a while loop, I just know what's going on instead of writing like 5 different subqueries with, correlated joins. And in the end, it's kind of, what is this query even doing?
Yeah. So I think there's a big missing piece that we said we were going to cover at the start that I have to ask you about, the whole exactly once semantics question that we punted that you don't want to implement yourself. You want your stream processing library to do. So, Matthias, take me through some of that.
Yeah, I think one aspect is again state. I mean, if you do exactly once processing, you also need to include your state. So if you modify your state during processing and something goes wrong, then you need to be able to roll it back. And then the question is, how do you do this? And especially when we integrate with Kafka here, so Kafka does have transactions, and those transactions are designed in a way to say, well, I basically have an atomic operation that allows me to publish my result records into the output topics and also record the input offset changes and makes this an atomic operation. So either the offset and the output both make progress or both don't make progress.
Now that seems
now
like
you have
something.
State,
Sorry.
right? And you also want to maintain state, but state is kind of now an external dependency. Even if you use RocksDB, we have it as an external dependency. And then you basically say, well, I could use transactions on my state backend. Sure, but then you have 2 transactions going on, so it's not atomic anymore. And then things starts to become very complicated.
Then you're reinventing 2-phase commit just in your one state processing app.
Something like that, exactly. And I don't think you want to build a 2-phase commit protocol yourself.
I neither want to build nor use one.
I think Kafka has guarantees in this regard as well, in terms of, if I publish data to the topic, I know that any consumer can access that data, and they're going to get the number of events that was published to the topic. They're not going to get 0 events or duplicate events if I've published that. And that kind of guarantee is really critical and makes stream processing easier. In Flinkland, if I'm reading from a Kafka connector, I get all those guarantees that Kafka brings. But now if I'm reading from some other connector, I lose them. And now I'm joining 2 streams in Flink. One of them has these guarantees, the other one doesn't. And now it's on Flink to ensure that this is end-to-end exactly once. There's capabilities in there for that, but it's painful.
Okay.
Yeah, absolutely. Yeah, I mean, that's the advantage of Kafka Streams and ksqlDB. Deeply integrates with Kafka, so you don't have to worry about other things because you control the full ecosystem. And in Flink, you integrate with everything, and then it's kind of, well, what do you do?
Yeah. So let's just step back to finish up. Jeff, this is probably a question for you. Do you think there are businesses or customers or places where one is a clear choice over the other? Are there certain kinds of use case where you'd say, okay, that's one we should take with Flink, or this is clearly only going to work in KSQL, or is it more kind of a taste thing?
I think it's a gradient thing. I think you can look and see who's adopting it, right? And that gives you a clue. Most Confluent customers doing stream processing can do it within the context of Confluent. A lot of Confluent customers are not doing stream processing yet, and they 90% of the time will continue to do it within the context of Confluent. The outliers are the interesting ones, and they tend to be web properties with super massive scale and super big state doing crazy aggregations. I know Netflix uses Flink for sessionalization, all their session kind of stuff. I know Epic Games uses Flink as well for a lot of stream processing on their back end, even though they're Confluent customers. So I think there is kind of a developer-heavy, very custom aggregation at super massive state and high scale, where Flink starts to look better. but you don't really know you're there until you're deep in stream processing territory. And I think most of the time you're not going to get there. That's my take. I don't know, Matthias, if you have a different one.
No, I agree. I mean, Flink can be a little bit more efficient the way it's built, but it also puts much more burden on the developer to actually get to that level. So if you take say Netflix and an Epic game, and I think Uber, they basically have like stream processing teams. They only do stream processing, and those teams become stream processing experts. And that is the reason why they can leverage Flink in that way. If you're an average developer, you might not have the skill set to do that. And then using something like ksqlDB is just simpler, or Kafka Streams. And usually you don't need to scale anyway, because it really is this kind of, outliers that have this, massive amounts of data. For most people, even if you use Kafka Streams, it basically kind of idles around. It's kind of, whatever, give me your events. I'm bored anyway. So, because it's still high performance. I mean, Flink can still be like 10x more, but if you only use 1% of Kafka Streams, then you would only use 0.1% of Flink. So what do you gain by using Flink? You don't need it.
Yeah, sometimes it's the complexity of the transformation, not the throughput of it, right?
Yeah, exactly.
Yeah.
And then, of course, in the end, I mean, it's also a question, how you want to run and deploy. For example, ksqlDB, I mean, we offer it at Confluent as a fully managed service. There's no really such a thing for Flink. And then it's kind of, you get support and, you don't worry about it. You don't need to worry about the deployment. So those things are also very important to consider, obviously. If you just, want to get your job done and not become a deep stream processing expert.
Yeah. I don't think anyone wants to before the day they need to, do they? Maybe. I don't know.
Yeah.
But you get this, perhaps a final thought. I was building something recently with Confluent Cloud, and you get this. To me, it still feels strange. I go and look in the console, and I've got insert into blah and a select query. I've got an insert select from, and that's just running in the background. And I still find this a strange new world in some way. That insert to select isn't a one-shot thing. It's like this running process.
I don't trust it. Like it's being a Confluent has had to teach me to trust these things. Like I'm used to, Tim Berglund did a video, and he was still with us, on the guy who needed to have his hands on the bare metal and really introspect. Like it's a fantastic video. You should look it up. I wasn't that far along, but I do like to tail a log file, right? And I want to be able to tail the log file of the connector and tail the log file of the running query, and then see if the hardware is getting in the way somehow. And trusting that this is just working, and sort of removing my grip from that log file so that I can just look at the data as streaming off of a KSQL query as shown in Confluent Cloud it's scary, but it seems to work so far, and I'm pretty happy with it.
Yeah.
And to be fair, I think so the most use cases we still have is where you have like upstream ingest, and then you process with ksqlDB. So that you have like client-side ingest. I mean, we have the capabilities to do that. But I think that this is, very good for demoing and stuff like that. I'm not sure if anybody's using it in production at this point. I think there's a good thing we see a lot of use cases in production that actually query the state. So you have your persistent query running in the backend, it's maintaining a table, and then clients are coming along to do lookups into those tables. So that is a very common use case where the client interaction comes into play with the ksqlDB backend. But it's more on the read side than on the write side for production use cases at the moment.
Yeah. I've played around with some interesting stuff like building dashboards where a lot of the logic of the dashboard is just a table select, rolling through that stream of events, building up a table. And then you can finally write your app as I'm just going to select from that table at the end because all the state's there and processed.
Yeah, exactly.
Well, I think we should leave it there, and I'll part with some advice to Jeff. If you ever get that hankering to tail a log file, all you need to do is select star from stream emit changes. That will feel exactly the same.
Thank you.
Thanks very much, Jeff Bean, Matthias Sachs. Thank you for joining us.
Thanks for having us.
And there we leave it. And genuinely, after this recording ends, I'm off to go and work on my own stream processing project, so I'll be writing some KSQL in a few minutes. Before I go and do that, let me say that streaming audio is brought to you by developer.confluent.io, which is our educational site. There are courses there for KSQL, Kafka Connect, Kafka Streams, some of the other things we've been talking about today. as well as one that takes a look at ksqlDB under the hood, if you like gory details. So have a look at those, and if you need a Kafka cluster to use while you're doing some of the exercises, register a Confluent Cloud account using the code podcast100, and you'll get $100 of extra free credit. And they'll know we sent you, and that completes the feedback loop. If you want other ways to let us know you're out there, please get in touch. My contact details are in the show notes, or you can leave us a review or a rating or a thumbs up or a comment or 5 stars, whatever feedback mechanism your favorite podcasting app offers you. I would love to hear from you, so please do use it. And with that, it remains for me to thank Matthias Sachs and Jeff Bean for joining us, and you for listening. I've been your host, Chris Jenkins, and I'll catch you next time.